Hi, welcome back to my video series. I wish I watched this video when I started learning about AI. This is explain-05, and let's get started with the presentation forthwith. The test draw function generates exactly the same expression as before. We're just going to be using the value class that we used before. Okay. These are the same graph fields that we saw before. Now we're doing tinytorch.tensor just as a demonstration. As you can see, it looks exactly the same as before, but since we haven't done the backwards yet, the grads are all 0. Okay. So now we do the backwards operation for V1 and draw it. And as we saw, the grad values are exactly the same as when we did this in part 3, or explain-03. Now let's do the backwards of V2, which uses tinytorch.tensor, and print it. It has the same grad values as V1. As you can see, b.grad is -4, b.grad is -4. Now, what are we doing here is I'm printing out each thing in V1 and its .grad field and double checking to make sure that the gradients are identical. And lo and behold, it is. So that's good. Now, just for giggles, I'm printing out V2's label, the op, and prev. Okay? That's what they look like. Okay, so remember, if you're sort of confused by what the op and the prev fields were in when we did the value class before, that's basically what they look like. Remember, tinytorch tensor is just a toy tensor class. In real work, you would use torch.tensor. Okay. Now, what we're going to do is we're going to redo the prior example we did in explain-03 of a simple three-layer perceptron. The major difference from last time is that we're going to represent the W and B using vel type. And vel type will be the tinytorch tensor or PyTorch tensor. We took pains to make sure that at least the very basic PyTorch isms are supported in tinytorch. This layer class, actually something that is very similar to it, is actually available in PyTorch, but I'm showing you how to implement something like it, or something like what PyTorch actually gives you, so that you'll understand what the PyTorch layer class is doing. It has a call method, which actually does the calculation. Note that the layer is a class, not a function, but the call method allows us to treat an instance of the class as if it were a function. This is a Python-ism that you'll have to get used to. The function parameters, this function parameters is very important. It allows us to examine the parameters of this computational layer unit later on. PyTorch layer class also has this method as well. Now, for the MLP class, it has n in, number of inputs, and n outs, which is the number of outputs for each layer. The variable SZ is simply an array of the shapes of each layer, starting with n in. So the ith layer is of shape SZ sub I, comma, SZ sub I plus 1. Okay. And as you can see, it's initializing s dot layers, which is simply an array of layer that we just defined, using the sz to define the n in and n out for each of the layers. Okay. XS and YS are exactly the same as what we saw earlier. Each row of XS has 3 elements or 3 columns. Because the MLP that we're creating will have exactly the same number of inputs as before. YS has 4 elements, 4 columns, or 4 expected values, one for each row of XS. The build MLP method helps us to build the MLP that we want, or the multi-layer perceptron that we want. And do pass is the training loop that we saw before, but with a little bit of a twist. Once you begin to examine real PyTorch training code, it'll look very similar to do pass. The thing that will change in real Python code is this section right here. This is the part of the loop that updates the .grad field for each of the parameters. That in real PyTorch code, updates the data field with respect to the values from the grad. That portion in PyTorch code is the job of the optimizer class, which we'll cover in a later section of the video. For now, we're starting the we're still using the mean squared error, which actually gets used in some real NNs, but usually not in LLMs. We'll see the error function for LLMs in the future video. The LR, oops, where is it? Right here. The LR in do pass is the learning rate. Parameters like this are sometimes called hyperparameters. Again, just a fanciful jargon. Just get used to it. Remember that the LR is used to scale the grad values to add back to each of the parameters. In real PyTorch code, you'll likely vary this learning rate according to some schedule. We'll see examples of doing that later as well. But for now, our very simple neural network, this loop is sufficient for it. Oh, ignore the debug pop. It's just an artifact of a very early debugging aid pattern that I came up with years and years ago. You won't see it anywhere else other than my Python code, so you don't need to worry about it. Let's build a neural network using build MLP. As in part 3, we're building a 3-layer multi-layer perceptron. It's the exact same size and shape. Do not forget to initialize the random number generator. Otherwise, your experiments will not be reproducible. Inability to reproduce results is the single biggest failure in the scientific endeavor for nearly everyone. Unfortunately, this experiment will not have the exact same results as before. Why? Because the order of initialization is different. Meaning the order of the initialization of weights are different. Let's jump back to part 3. Okay, so what do we do there? Okay, here we are. In part 3, we initialized each neuron separately. In other words, the W and the B for each row. Whereas now, what are we doing in here? We initialized all of the W's for the entire layer first. Okay. Then the bias. Repeat, we initialized the entire matrix W first, then the bias. This means that our starting values for the layers will be slightly skewed. You'll run into issues like this all the time as you play around with your neural network design. You just need to be mindful of it. We're creating N1 and N2. Okay. With torch.tensor and then tiny torch.tensor. And the idea here is that between the two, the outputs should be identical or as close to being identical modulo numerical stability. As you can see, each item for the output of N1 and N2 are pretty close to each other. 7.874, 7.874, so on and so forth. Final result being 0.00668, 0.668. Okay. Now let's draw the computational graph. Oops, where's the computational graph? I'm sorry. Oh, skipped it. Sorry about that. Now let's draw the computational graph of A2. As you can see, even this simple multi-layer perception already has way too much math for humans to deal with manually. I jumped ahead there. We are recreating N1 again because now we're going to use the do pass to calculate the results. And we recreate N2 using tiny torch. At least visually, the individual loss values are nearly identical for each operation. Right? And this is really good sign that we're doing something correctly. And lo and behold, when we calculate the difference between L1 and L2, we're pretty close. So that's really, really good. And that concludes part 5. So what's with the tiny torch.tensor? It's useful if you want to learn how you might implement some of the fancy tensor access logic. It's small enough that you should be able to study on your own. You would not use this class for any real neural network work because it's not optimized at all. You would use torch.tensor or PyTorch tensor. But at least for me, while I was learning all this, implementing a small subset of PyTorch really helped me to understand what is going on underneath the hood. And this concludes the first 6 sections of this video series. We covered the basics of calculus, the secret to how neural networks actually work, and we explored how backpropagation works in literally less than 100 lines of code. Thank you very much. We will see you soon in the next chapter, which is going to be part 2.